Yes.
So when is your next homework due? Is it next Friday, I think, or is it next Monday? I mean, Monday the 1st.
I believe
Monday
it's
the
next.
8th.
It's March 5th.
March 5th. Okay. So that's a Friday, right?
Yeah.
Yep.
Okay, so that means you need another homework by Monday.
Yes.
Okay, I'll make sure that happens.
Take your time.
You want to get your money's worth, don't you?
That's true. I mean, we're getting our money's worth so far. But...
Oh, I don't know. Not that you should have probably more homework than you're giving at the moment.
I don't know about the rest, but I'm happy with the amount of homework, you know.
Yeah, the problem is whatever I give out, I have to grade. Okay, let me share my screen. Okay, my screen should appear full now. Is it true?
Yep.
Okay, great. Just wait another minute, then we'll start. Okay, time to start. So this is where we got to last day. We're talking about accelerating rate calorimetry, and this is the temperature versus time plot for lithium cobalt oxide reacting with the electrolyte. This material is charged at 4.2 volts. If you charge it to higher voltage, it will begin reacting at a lower temperature. And the key is to try to understand these curves and learn about the reaction kinetics going on between the charged electromaterial and the electrolyte, and then be able to make some predictions about what real cells should do with those reaction kinetics in hand. So usually what we do, I should go back, usually what we do is we plot the self-heating rate, which is the rate of change of temperature versus time versus the temperature. You know, so here the rate of change of temperature with time is small at low temperature, and then the rate of temperature with time gets really large at higher temperature. So we plot the logarithm of the self-heating rate versus the temperature. And this blue data that you see is for the experiment that was on the previous slide in black. And what are these other curves that you see? Well, these are curves that were measured where the accelerating rate calorimeter was directly forced to 160 degrees C, to 170 degrees C, to 100 and I don't know, some other temperature, 175 maybe, and 180 degrees C. So what that means is we forced into a range where the reaction was already going at an appreciable rate. And that's why the self-heating rate is appreciable at that temperature. Okay, so we need to consider for a moment what should happen when we force an accelerating rate calorimeter, to a higher temperature. What should we see? So let's do that. So we'll plot the self-heating rate versus temperature, and we'll assume that there's a first order reaction going on. So we mentioned before that what happens here is you have the total heat involved in the reaction, that's H, times the frequency factor, times the Boltzmann's factor, then 1 minus U. And you remember U is the degree of conversion of of reactants into products. So at the beginning of the reaction, U is 0, and at the end of the reaction, U is 1. And then all you have to do is recognize that the self-heating rate is the power divided by the specific heat times the mass of the sample. So you can calculate the self-heating rate. That gives you a change in temperature. You can calculate a new temperature, and you can calculate a new change in U. And you can get these curves. So this one starts at 150 degrees with the circle. The square starts at 160 degrees, and the triangle starts at 170 degrees. And you see this self-heating rate that increases, almost exponentially, slightly less than exponentially because of this 1 minus U term. And then as the reactants run out, the self-heating rate it just ends. Some people like to think of reactions with zero order kinetics, which means you don't worry about the reactants running out, and you just have H times gamma times the Boltzmann's factor. There is no 1 minus U term. And then if you start at 150, 160, or 170, you follow this curve, and then when the reactants are gone, you drop off the map. And you still keep track of how many reactants are around, and when they're gone, the heating stops. So the thing that you should notice here is that when you start heating from a higher temperature, the behavior falls sort of on the same path that the 150 degree heating did for zero order. And here, if you draw a line through the start points, and you call that the Arrhenius line, at the start points, U is 0 for all of these, and these would fall, if you plotted self-heating rate against 1 over temperature in Kelvin, they would fall on a straight line. And over a narrow temperature range, plotting the self-heating rate on a logarithmic scale versus linear temperature falls almost on a straight line. So the point is that these curves fall to the right and below the starting point of an experiment that starts at a higher temperature. Okay, that's what happens, because by the time you get up to this temperature, you've lost some of the reactants. Some of the reactants are gone. U is greater than 0. So this term, the whole term, is less than it would be for when you start at 160 degrees compared to 150 degrees. If you remember the previous data, it's not the case. If you draw the line through the starting points, you see that the self-heating rate is to the left and above the line through the starting points for them all. Okay, so this was a surprise. It doesn't follow just simple reaction kinetics. Does anyone have any questions about that? Is what I'm saying clear about the way the data looks quite different than the expectation of a first order reaction kinetics? So you have to ask the question, what the heck is going on here? Okay. How the heck can the reaction move above the Arrhenius line? I think there's a spelling error here. How does this happen? So if you have an autocatalytic reaction process where something decomposes in the presence of something A, and you create more A as well as other products, then this reaction accelerates as it continues because you keep making more of this catalytic material A. That's called autocatalytic, all right? And you can explore what happens if you think about the reaction between lithium cobalt oxide and electrolyte in terms of an autocatalytic process, not identifying what the catalyst might be, but just saying, okay, what would happen if this occurs? And what you do is you add to the experiment for the rate of change of the reactants into products an extra term over here on the right. So what is this extra term? This represents the fact that as the reactants convert to products, U increases. So this term that's in here increases to mimic the fact that as the reaction proceeds, it tends to accelerate as you create more of the products, and maybe one of the products is this autocatalytic species that's there. So obviously, if this term was simply proportional to U, at the beginning U is 0. There have been no reactants converted into products. So you have to start with some initial value, which can be very, very tiny. It might be 10 to the minus 3 or something. U varies between 0 and 1. And then you'll learn that this expression will create an accelerating rate calorimeter curve that looks a lot like an autocatalytic type of behavior. So we explored the presence of this term. Okay, so the self-heating rate in accelerating rate calorimetry, as we mentioned before, is the heat of the reaction divided by specific heat times the rate at which the reactants are converted into products. So you take the derivative of this term, derivative of this thing, and stick it in here. So if you think U is 0 at the start of the experiment, then this beta is the initial amount of this autocatalytic thing. Okay. And H is the heat evolved per gram when the change in U is equal to 1. Now you can also measure differential scanning calorimeter data. It's a different type of calorimetry where you just heat the sample and you measure the heat that it evolves. So you provide heat, you heat it at a constant rate, and what it will do is it will provide heat as the reaction occurs, and that heat will just be H times du dt per unit mass. So we use this expression for the accelerating rate calorimeter, for the reaction kinetics with these parameters. And we fit the accelerating rate calorimeter data starting at 150, starting at 160, starting at 170, starting at 175, and starting at 180. I would say those fits are pretty darn good, where no adjustable parameters, no changes to the parameters were made in between these different experiments. So that means you can describe the reaction between lithium cobalt oxide, delithiated lithium cobalt oxide at 4.2 volts, with electrolyte. All you have to know is the temperature and the value of U. Then you can figure out du dt, and from that you can figure out how much heat is being evolved.
Jeff?
Yeah.
On that last slide, how come your fit doesn't account for, the increase in temperature above like 210? Yeah.
Right. I was coming to that, and actually the next slide will be better for us to talk about that.
Okay.
So we also applied the same model to DSC experiments. So we heated 2 degrees a minute, exactly the same parameters that were used to describe accelerating rate calorimeter. And the experiment that you see has got 3 peaks, and our model has 1. So Ahmed's question goes to really, what are these other reactions that occur that happen after the first one? So here we're modeling the first step well, and then there's a second step and a third step that we're not modeling. So I'll go to my document camera and explain what's happening in this second and this third step, okay? And I'll just tell you that the way that we figured out what was going on in these steps is you take accelerating rate calorimeter and you let it run up to this temperature here, and then you quench the sample and you take it apart and do X-ray diffraction on it to see what has happened to the solid. And then you run over this peak and you quench the sample, you air cool very rapidly, and you take X-ray diffraction. And then you let it go to completion and you measure X-ray diffraction. And that's how you figure out what's going on. Alternatively, you could stop the DSC at this point, or at this point, or at this point, and examine the sample and see what's going on. So I believe you can see my document camera. Is it true?
Yes.
Okay. So let's just say we have lithium 0.5 cobalt dioxide to make it easy. That's about what it is at 4.2 volts, a little bit less. And then you apply heat and there's electrolyte around. What you learn is in the first step, this goes to 0.5 lithium cobalt oxide. So you get lithium cobalt oxide back plus, what is it?
Jeff, can you move
yeah.
move the paper down a little bit? We can't see the top.
Like
yep,
that?
thanks.
How's
Yep.
that? Okay. Plus 1/6 CO3O4. And then there's oxygen unaccounted for. So I've balanced the cobalts here. The lithium's balance, the cobalt's balance, and there's some extra oxygen. I don't know how much here. Some oxygen, Y02. And this is what combusts with the electrolyte. Then the next step is CO3O4 plus heat in the presence of electrolyte goes to 3COO plus more oxygen. And that combusts electrolyte. And then the final step is, with heat, COO goes to cobalt metal plus half an oxygen, and that combusts the electrolyte. So you get the full-blown reduction of the material that's not lithium cobalt oxide all the way down to the metal. 1, 2, 3 steps. Pretty crazy. So we're just modeling the first step. Okay, so we'll go back to the PowerPoint.
Jeff,
Yeah.
so just from the equations you have written on the piece of paper, I haven't seen any of the autocatalytic nature of the things, because for the autocatalytic reactions to happen, as you said, the product has to become a catalyst. But these 3 reactions doesn't show that.
Yeah, you're right, Wentao. I think the autocatalytic part comes about because of the presence of the products that are made in the reaction with the oxygen. You know, they just turn out to be more reactive, more effective at removing oxygen from this thing. You know, the presence of, like, if you just take lithium half cobalt oxide and do thermogravimetric analysis on it in argon, it doesn't thermally decompose like this until probably around 200 degrees C. But in the presence of a reducing agent like the electrolyte, meaning the organic solvent can combust, that helps to strip the oxygen out and drive this reaction at lower temperature. And I don't know exactly how all of that works. Really, what I'm telling you is that when we examine the samples and open them up after those 3 steps by X-ray diffraction, we saw that. And then we saw cobalt oxide plus lithium cobalt oxide, and we saw cobalt metal plus lithium cobalt oxide. How the autocatalytic thing works, I don't know.
Okay, thank you.
Is it possible for the reaction between oxygen and electrolyte to heat the environment more, which kind of forces more decomposition? Would that feedback loop be considered autocatalytic?
No, that's why the that's why the temperature goes up. You know, this is the reaction between the material, the oxygen, the materials evolving, and the electrolyte that's causing this accelerating rate. Okay, so anyway, the point is we basically have reasonable kinetics that can describe the first step of the reaction of the positive electrode material with the electrolyte. And this was a lot of work to do this. So I don't know if Inez is listening in, but you know, Inez has been doing some accelerating rate calorimetry, and she has not been trying to extract reaction kinetics. And in order to do so, you basically have to do these experiments where you start at different temperatures and look and see what happens and decide if you need an autocatalytic reaction or just the first order reaction is enough, or you know, whatever happens. And it's very useful to vary the mass of the sample, because sometimes you don't get to see all the features like this. We don't see all the features. What we would do is reduce the mass of the sample, and then the total temperature rise would turn out to be less because there's less reactants in the tube. Not only do you have to heat the contents of the tube through self-heating, there's also the stainless steel container that you also have to heat. And the small stainless steel container in the experiment, I think, weighs about 1.5 grams, and the sample would weigh typically, 100 milligrams or less. So the majority of the self-heating, the heat is used primarily to heat that stainless steel tubing up in temperature. So you have to take account for that in your analysis. The heat capacity that you have here, the specific heat includes the specific heat of the stainless steel tube. Anyway, enough. So then Dean McNeil did a lot of work and looked at different reaction models, 12 different reaction models, and tried to get an even better description of that reaction. And that's described in this paper. The details aren't really important. But what really is important is, what do? You want to figure out what happens to a full lithium-ion cell in an oven exposure test. So you basically do exactly what we did before for ditertiary butyl peroxide. So you need what are called power functions. This tells you the chemically generated power due to the reaction between the electrode materials and the electrolyte. You need to know the heat of reaction per unit mass, and you need to know the rate at which the reactants are being converted into products. This depends on the value of U, and it depends on the temperature. So you need those reaction kinetics determined from ARC and DSC. And you need them for the negative electrode and the positive electrode, okay? So that will be heat that's generated in the lithium-ion cell when it's heated to high temperature in an oven test. And then you have to worry about the heat transfer from the cell to the environment by Newton's law of cooling. We talked about that before. It's the temperature. Normally here, the cell temperature is going to be greater than the environment temperature. So the heat is going to be lost as the temperature goes above the environment temperature. So this term will be negative. And then you say that the rate of change of temperature of the cell is equal to the power that's generated chemically plus the power that's being dissipated. It's negative if the temperature is greater than the environment, and this is positive if the environment is greater than the temperature of the can. So when you place the cell into the oven, this is positive. The oven temperature is greater than the cell temperature. But then once the cell reaches the oven temperature and starts to go above the oven temperature because of the chemically generated heat, this term becomes negative. And you divide it by the specific heat of the cell, and you multiply by the mass of the cell. So it's very simple once you know what the reaction kinetics are. But determining those is a lot of work. And then you can make a little spreadsheet program to do these calculations for the oven test. And you assume that the temperature in the cell is uniform. And it turns out that this is a pretty good assumption for 18650 and 2650 size cells. And the reason is that the cells are filled with really fantastic high thermal conductivity materials. There's aluminum foil and copper foil current collectors throughout the cell. So it turned out when Tim Hatchard was really trying to determine the temperature difference between the core and the surface of the cell and the oven temperature, it really was just a very brief thing. Just hang on a second, I have to take this call. Hello. Yeah. Okay, I'll have to bring my trailer up from Lunenburg this weekend, and then I'll be able to come over next week. All right, thanks. Yeah, bye. Sorry about that. Yeah, so you can imagine the cell is a pretty good thermal conductor. So the first thing you have to do is you have to determine the surface heat transfer coefficient of the cell. So what you do is you put a cell or a stainless steel cylinder, anything you want, into an oven. So the oven was, I think, at 140 or 150 degrees C. And you measure the temperature versus time of that cylinder. That's the dash here. And then you use Newton's law of cooling, heating, shown here. And you calculate the rate of temperature of the cell, which would be this power transferred to the cell, divided by the specific heat of the cylinder that you're using and its mass. And by fitting the data, you can extract the surface heat transfer coefficient, which is what you have to be able to do these experiments right. And then you just go through this little process here. I think I describe it on the next, yeah, here we go. So you have a few things that you have to do. You know the chemically generated power due to the reaction between the electrode materials and the electrolyte. And we're going to assume that the negative electrode is inert. That's a poor assumption, but I don't want to make it very complicated here. I'm just going to worry about the positive electrode, and we're just going to say it's lithium cobalt oxide. And we're just going to worry about the first step of the reaction between lithium cobalt oxide and the electrolyte. So we know the reaction kinetics for that. For the autocatalytic case, you start with some initial value of U. So I called that beta before. But you can just start with some very small initial value of U here, and everything works fine. You have Newton's law of cooling. You know how the rate of change of temperature with time depends on the chemically generated heat and the heat transferred by Newton's law of heating and cooling. Seen this before. And everything else here that's in this equation, in these equations, you know. You know the total heat evolved. You got that from accelerating rate calorimeter. You know you start with U very near zero, and U increases with time. You know the surface heat transfer coefficient. You know the surface area of the cell. You know the oven temperature. You're going to calculate the cell temperature as a function of time. You know the frequency factor from your kinetics determination. You know Boltzmann constant. You know the specific heat of the cell, and you know the mass. So everything you need to do this, you know. And here are typical values that you're going to need for your homework when you work on this particular problem. And then what do you do? So what do you do? So you assume that at T equals 0, the temperature is room temperature, and there's some starting value of U because it's autocatalytic. So maybe it's 0.04. It could be something else, 0.02, 0.01. You can pick something. And then you pick a convenient temperature step. So temperature step of about 1/4 of a minute is good. And then you go ahead and start doing this. So what you do is you use this equation to calculate the change in U that takes place during a little bit of time. I guess I'll write it down. I'll write it down on my paper, and then I'll show you my paper. Delta U is H gamma e to the minus EA over KT, 1 minus U times U times delta T. Now I'll show you my document camera. You should see my document camera here. So the idea is, excuse me, there should be no H here. If you know EA, the starting temperature, starting value of U, and you're going to say in a quarter minute, sorry, what's going to be the change in U? You can calculate it. That's what you do. We'll go back to the spread, to this PowerPoint. So we calculate du dt and du. And if we know du dt, we can calculate the chemically generated power. You put that in here, H times du dt. And you know the temperature at that time, so you can calculate the power that's either being added from the environment if the temperature is lower than the oven temperature, or the power that's being dissipated to the environment if the temperature is greater than the oven temperature. And then you have to get delta T. So how do you get delta T? You go to equation 3 and you write the following, which I'll show you in a minute. Actually, I can show you now. Pchem, what did I call this? Pchem over Cm times delta T. So for a small time step, you calculate the change in U. You calculate all these other things. You calculate the change in temperature that takes place in that time step. And then you add the change in time to the original time, the change in U to the original U, the change in temperature to the original temperature, and you'll go back to the beginning, and you just keep repeating all this thing until all the reactant is converted at U equals 1. So it's straightforward with a spreadsheet calculator to solve these equations. And if you do that, this is what you get, okay? So this is temperature versus time for a lithium cobalt oxide 18650 cell, charged at 4.2 volts with a heat per unit mass for that first step of the reaction of 300 joules per gram. If the oven's set at 130, you put the cell in the oven, perfectly safe for a long period of time, 10 hours. At 140 degrees, you put the cell in the oven, you'll see a reasonably, you'll see a peak in the self-heating. And at that point, this should be U. I used to call it alpha. At that point, the reactants are converting into products rapidly when the temperature goes up. That's because all these reaction rates increase exponentially with temperature. But if you put the cell in at 150, it goes into thermal runaway, and if you put it in at 160, it goes into thermal runaway. Any questions about this?
Yeah, Jeff, quick question. So in practice, the ARC might be more representative of what happens because cells are in a pack, and it's safe to assume that all the cells are going to behave the same way, right? So they're sort of in a environment where they can't really dissipate heat from the can. Is that a fair assumption?
Yeah, provided there's no way for them to dissipate heat at all. If you have no external cooling and the cells are just locked in a giant pack, they can transfer heat to the neighbor. So if only one cell is having, say, an internal short and generating heat, it will transfer heat to its neighbors, and that will help to mitigate its temperature rise. But if you put the whole module into an oven, you know, eventually the cells in the middle will come up to temperature. And again, they can still transfer their heat to their neighbors, but their neighbors are already really hot. So things are gonna go out of control. You know, this is really, you know, if you wanted to simulate that, you just have to change the way that the heat dissipation occurs. You know, here we're just saying the heat dissipation is very simple. It just depends on the oven temperature and the cell temperature. If you had some more complicated setup, you'd have to change this term, which deals with the heat transfer to the environment. Okay. Any more questions about this?
So is there any advantage to doing ARC versus like a conventional, you know, bomb calorimetry experiment where you can also increase the temperature and monitor the change in heat? Or is it like, why are we using, you know, this, you know, big bulky ARC instrument compared to like conventional bomb calorimeter?
Well, a bomb calorimeter doesn't give you any information about kinetics. It just tells you about the total heat that's being evolved. You know, if you had a calorimeter, okay, what is an ARC, right? It's just, really all it does is measure the self-heating of the sample due to this reaction in the situation where there's no heat loss to the environment. So if you had a bomb calorimeter and you were measuring the temperature of the reactants and you knew exactly how much heat was being transferred to the environment at any temperature, then you could back all this out. It's just a lot easier to do it when you know the heat transfer to the environment is zero in the ARC. It's a lot easier to get the kinetics. Is that useful?
Yeah, that makes sense. Thank you.
Okay, so then as sort of a first approximation for what happens if you include all three steps in the reaction between charged lithium cobalt oxide and the electrolyte, then you increase the heat of reaction to 700 joules per gram. And this is sort of approximately okay. And what you see in that case is you go into thermal runaway at 140 degrees C, whereas with a lower heat of reaction, you did not go into thermal runaway at 140 degrees C. And 127 degrees C is just about the limit where, you know, if you go to 130, I think this cell will go into thermal runaway eventually, maybe at 300 minutes or something. So Tim Hatchard made a full thermal model, basically along the lines that I'm talking about, except he also included heat flow in the cell by the heat equation, where he did not assume that the cell temperature was uniform everywhere. But after he did this, he learned that the cell temperature was virtually the same everywhere in the cell. So this turned out to be not really that much of an advantage. And then Tim used his software and kinetics that were determined by Dean McNeil to try to model what happens to an 18650 cell from Mali Energy, which had lithium cobalt oxide in it, and use the electrolyte, the same electrolyte that we characterized in the ARC experiments to get the reaction kinetics. So these are oven tests at 140, 145, 150, and 155. And you can see the data here and the model predictions here. So the model predicted at 155 the cell should go into runaway, and at 150 You can see there's a fair amount of early self-heating. Happens a little bit earlier than happens in the moly cell. So the point of this was for us to get a reasonably decent understanding of what happens in the thermal runaway of a lithium-ion cell in an oven test. Oh yeah, I should mention, what is this thing here? See that little glitch? That's when the safety vent of the cell opens and electrolyte vapor comes streaming out. So you're evaporating electrolyte and you get a little bit of cooling. So that isn't captured in the model. So if you look at the data and you said, okay, let's project this upward without that little glitch, it probably would have looked a lot more like the model did. And the other thing you'll notice is it looks like the experiment goes to some massive, humongous temperature, whereas the model does not. In the model, we didn't include the negative electrode side. It was just the positive side. Yeah, and this is another thing that Tim did. He used his model to calculate the impact of cell radius on the oven test. So this is a 160 oven test for a lithium cobalt oxide cell. And I'm not exactly sure what is happening relative to the kinetic equations that were used here, but the point of this was, with a small diameter cell, you can get the heat out. There's enough surface area to get the heat out and you don't get thermal runaway. But as you make the cell diameter bigger, the surface area to volume ratio gets smaller and smaller and you get into trouble. So, this is where people should worry about making very large diameter cells, because it's much harder to get the heat out. And safety-related issues become much more interesting to deal with as cells get larger. Okay, so this work's described in these papers. You'll get a homework assignment on this type of stuff. All materials are not created equal. NMC materials, this is an old slide. I don't know what it is now. 500,000 tons per year at least, I guess, are used today. So these are ARC experiments that just show if you try to follow the ARC over a larger temperature range for lithium cobalt oxide charged to 4.4 volts and NMC charged to 4.4 volts, you can see that you start seeing self-heating at an appreciable rate with lithium cobalt oxide, even down at pretty low temperature by comparing to some of the NMC grades. So people just don't use lithium cobalt oxide in big cells. It's more reactive than NMC. We have just a few minutes left. Yeah, I wanted to just show you guys this particular test. This is a test that's Japanese Battery Association likes people to use. The International Electrotechnical Commission came up with this test. This is a test where you can probe the short circuit behavior of a cell. So you're trying to create an internal short. So you have a pouch cell and you unroll the outer wrap and you put this nickel particle, which has a particular shape in millimeters, on top of the separator, and then you close up the pouch again, and then you fill it with electrolyte and you do the formation, and then you crush the cell between flat plates, and that will create an internal short, and you can't have fire or flame. Okay, so this is a test. I'm not sure how often it's actually done, but pouch cells are supposed to have this test done to pass the IEC, to get IEC certification. This is the most insidious type of failure that you could get in a module. is where if you get side rupture of 18650 cells in a module, one cell gets hot, goes into thermal runaway, ruptures from the side, and then just causes its neighbor to go. And then you get propagation, it's called, from one cell to the next, to the next, to the next. It's much preferable if your cells are lined up like this to have any smoke and flame come out of the ends, then it's less likely to get propagation. So side rupture is a disaster, and it should be avoided at all times. Now, this is a slide taken from a presentation given by Henry Mao. He's the CEO and CTO of a company called Ulion in China. They make cylindrical cells. And he gave a lecture here a couple years ago about how you limit EV fires. And there was a lot of discussion about various things that can lead to cell venting and preventing side rupture and so on. But it was actually interesting. He concluded his talk with this slide. Tesla Model 3, a giant step forward in battery safety. So the cells are designed so there can be no side rupture. And I'm not sure what this means, same side wire bonding. I don't know why this is important. But all the cell openings are covered with fire extinguishing material, so that if one of the openings goes up, there's a lot of fire extinguishing material here to help prevent propagation and spread of fire. So at his company, they took a Model 3 apart, extracted the modules and took a careful look inside to see what was being done. And this is what people are doing all the time. They're engineering the battery packs to be more and more safe. There's only so much you can do at the cell level inside with the chemistry. You've got this reactive electrolyte that reacts with the charged electromaterials, and you have to start changing cell design to have things happen in your favor, and put in these mitigation things here as well to make things better. And it's quite incredible how safe the electric vehicles can be with all this good engineering going on. All right, so that's the end of this safety section. I'm going to do a section on electrochemical impedance spectroscopy next. It'll take a day or maybe a day and a half. And then I'm going to do a section on what's called differential voltage analysis. That'll take a day or a day and a half. The people in Lucas Swan's group, Riley Cook and others, I can't remember their names, that took the class last year, really loved the differential voltage analysis part. They used it in their theses. People in our lab use this all the time. So it's good for everybody to get exposed to it and see how it works. I'll share software with you that you can keep and use in another homework. And then after that, we're going to talk about aqueous metal ion batteries with liquid electrolyte. So we'll be moving away from lithium ion at that point. That'll take a day or two, and then we'll start on fuel cells. So we're coming to the end slowly of our long section on batteries and lithium ion batteries. Oh yeah, I've also requested for Mark Overbeck to give us a guest lecture on silicon and silicon alloy negative electrodes, and that'll fit in there somewhere also. Okay, any questions before we end? Comments?
Jeff, I just compared the ARC data you presented in this class with the ARC data presented by Hong Li yesterday on solid-state batteries. Looks like all the solid-state batteries, their kinetics is zero orders. It's like straight line. But for the liquid electrolyte ARC data you presented, all of the data seems to show this self-catalytic nature. Is this typical for is this difference like typical for solid-state batteries and carbonate liquid electrolytes?
The autocatalytic feature, I think, is really most common with lithium cobalt oxide. You know, the other positive electrode materials and negative electrode materials don't really show a lot of autocatalytic behavior to my memory. I don't remember Hong Lee's ARC data, and I don't know if it was for a full cell or just components reacting with each other. So I can't really answer your question, Wen-Tao.
So for the LFP cells, they don't have the so-called autocatalytic nature. They're like more like first order kinetics.
LFP really is almost inert relative to electrolyte. So the positive electrode side in LFP virtually does not react with electrolyte at all. So in an LFP cell, all the self-heating is coming from the reaction between the negative and the electrolyte.
I see. Thank you.
Any more comments or questions?
Yeah. How would the model that we talked about today capture temperature onset for the decomposition of cathode materials, if it does?
Yeah, it does. So see this? When we're talking about ARC, we talk about a particular onset temperature, whatever it is. And the onset temperature that we use in ARC is when dT by dt is greater than about 0.02 degrees per minute or 0.03 degrees per minute. So all you have to do is say, okay, look, well, you need to go back to the ARC expression, not the full cell. Back to the ARC expression, it's the same thing. Yeah, here we go. So all you have to do, Aaron, is just calculate this thing. You know, it depends on your starting value of U and all the other kinetic parameters, but you can calculate dt at any temperature for any value of U, and when that's greater than your onset, so-called onset temperature, your onset heating rate, which is 0.02 degrees per minute or whatever, you can figure out what temperature that occurs at.
Okay, thanks.
All right, well, this stuff will become more familiar to you once you do a few simulations of your own. You'll see how it goes, and I think it's useful because it gives you an appreciation of, you know, why you end up with thermal runaway in these types of cells. All right, so I'll stop there. We'll be back Monday. We'll start